Okay. Okay. So let's start. So hello everyone, I'm Alex, so thank you very much for coming. There's a lot of people in today, so this is very exciting, I think, for everyone. Today I wanted to talk to you about game AI, and in particular this algorithm that's called MiniMax, and it's used for two-player games when you're playing with someone else and you want to maximize your winnings and minimize their opportunities to counter you. So that's more or less what we're going to try to do today. So before we get into it, little introduction. My name's Alex. I am a software engineer. I'm doing a master's in AI and in big data. I'm also a student at 42 Madrid, for those of you who might know the 42 network. And I'm also currently working as a data engineer at Quantori. But that's enough of me, right? Let's get to the games. So, what games are we talking about? We're not talking about League of Legends or StarCraft or those sorts of games. We're talking about more simple games. We're talking about chess. We're talking about checkers. We're talking about tic-tac-toe. This algorithm is a really powerful algorithm. It was used in 1997 by Deep Blue. It's a research team at IBM. And they beat Garry Kasparov when they were playing chess against him, the grandmaster of chess at the time. And they managed to beat them using this algorithm, right? So you can use it on chess, is a really popular example, but also more complex games with more complex patterns like Go or Gomoku, checkers, any game really that's two players where where it's turn-based and when everyone has access to the same information, where we can all see the board and everyone understands what's going on and there's no randomness. You can apply these sorts of games. These board games, really, they apply really well to it, but also you can do it for video games if you're doing a turn-based game, right? So let's go over a little bit how the algorithm works. So we're trying to maximize our advantage and minimize the opponent's advantage. So I hope everyone can see the code more or less well. I'll go over it with you as well. So we call the function, it's a recursive function. It's a function that will call itself over and over again, right? So we start at the beginning, where we call min-max, and we give it the game state, right? The first variable is the game state. What is the game state? For example, in the picture we have right on the side, where you have a chessboard. That is the game state. What is going on? What are we playing? We're playing chess, right? Who am I? I'm playing white, and it's my turn to move. Okay, that is the game state right now. What is the depth of that we are playing in? So what do we mean by that? Is that when we have a tree, we're going to make a tree of the different possibilities that we have for making those moves. So as we explore the tree, as we explore the moves that we are able to do, we will increase the depth. So we will look how many steps ahead we want to move. So when you play chess, this is something we do when we play chess, for example. When we think, okay, I'm going to move my pawn here, but he's going to counter with something else. So maybe I shouldn't do that. Maybe I should do this other thing. That is basically what this algorithm is going to explore in real time, right? Also, we have our break condition. So it's a recursive function. It will call itself into infinity. So we want to break that at some point when we reach a depth that we want to get to, and when we finish the game. When we do a checkmate, then we don't need to explore that part of the tree anymore. And then right now we are trying to maximize our winnings because we are white and we're playing for whites right now. So we want to maximize our player winnings. So we're going to go into the first if over there. And what we're going to do in this function that's called get positions in the for loop, we're going to get a list of the moves we want to make. So picture the knight, right? We're looking at the white knight right now. He can do, in this example, two moves. He can go next to the queen, or he can go into the center, more or less, to attack both pieces. Which is the best move for us? What are we going to do? Well, we're going to go through each one of those, and we're going to explore how good or how bad we're going to do. So we go one level deep. So we go, if you see for the 4, and it goes, it's going to move all the positions. So our knight moved. We're going to see how it goes if we move our knight here. So that creates a new node, that creates a new reality, right? Which is the child node that we just created. We moved a piece, right? What happens now? Well, now it's their turn to move. So we've changed the game state. The state of the game has now changed. The depth is now one level lower because we're exploring a new move. And now we're no longer maximizing the player because now we want to minimize it since it's black that's going to move right now. So if you were a chess player and someone did this, if black moves, then obviously they're going to eat your knight, right? That is the most effective move that they could do to counter you. And what we do now is we've reached a depth of 2, which triggers our if function. So the depth function is, we're now going to do a static evaluation of the board. What does that mean? We're going to take a look at the board and say, hey, how good or how bad is this position for us right now? Is it a good position? Well, we just lost the knight, so it's not a very good position. So what we're going to do is assign it a value. So right now it's at -2. We did very bad. We lost a piece. Maybe that wasn't a good move, right? So what happens now? Well, we've reached the child node. We already know the score for that branch, for that outcome that we just explored. And now we're going to go back. Since it's a recursive function, we're going to go to the previous node and explore some other options. So maybe another option for black, right? Because we're playing black right now. Instead of eating our knight, they could have moved their knight here, which would make no sense because now we can eat their queen. So it gives us an advantage. So really what's going to happen is we are going to take the best moves that they do, right? Because we assume that they're going to make the best choices for them. And we're going to assume that we are making the best choices for ourselves. So by the end of it, we are going to say, they're not going to do this, right? They're not going to let me eat their queen. So this is a bad move for them. So we're going to pick for that level of the tree, we're going to say he's going to do the previous move where we lose points. And we don't really want that. So you explore the different moves that the AI, that the other player might do. You explore how well or how better off you're going to be after you do those moves. And then you do the entire tree, where you try different moves. You try you moving this piece and then countering it, and then you countering them, and then you explore the tree. This is a simple tree. It's a binary tree as well, so you only have 2 options, like here or here. But when you're doing a lot of pieces and you're doing a lot of different games, you can have a very big tree, a tree with a lot of child nodes. So you can imagine it gets really big really quickly, and it gets really complicated and also very slow when we're trying to optimize for this. So that's more or less how the game works. You essentially explore your options. You say, hey, I move my pieces here and they're going to counter with this. These are the scores we assign to each value, and this is the result. And we're going to pick what is best for us. So what is best for us is, for example, in this example, we explored the tree to the left, and that wasn't very good because we got a -1 out of it, so we lost some pieces. And then we tried some other movements, some other side, and we got a -1, which is better than -2. So we're going to pick the path where we lose the less amount of pieces, right? Or if there was a positive number, we would get an advantage there somehow. So that's how the algorithm works. It's kind of maybe disorienting a little bit because it's recursive and it calls itself, and you have to map it out in the tree. But I feel like it's actually pretty intuitive as how you score the values. But the thing is, the most important part of the algorithm is scoring the values, right? Because in chess, it actually, you can make it even more complex, but it's pretty simple because you always have a point system. So you say, I'm going to count how many pieces I've eaten and how many pieces they've eaten, and I'm gonna see if I have more advantage or if I have less advantage. So obviously you need a scoring system, and the king, obviously if you manage to capture the king, you win, so it has to have the high score, and then you go from there. So it works great as a value system in chess, since you'll be able to have an easy way of scoring points. But for example, for other more complex games where there's patterns that you have to see, where some positions are better because I'm in like 10 moves, I'm going to be in a better position to beat you. That's more difficult to actually see and actually program a function that can evaluate that correctly. So the most important part of this algorithm is not really the code that we have here. This is, that's it. That's the actual code. But it's the evaluation function that we were talking about, and that actually scores the points. That's going to be the more complex part of the algorithm. So a weak evaluation function is a really weak AI to play against, right? And then one of the things you can imagine is a problem is this tree getting very big, because we have to explore a lot of movements, right? Because if you're thinking about chess, you have 2 options. You can look many points, like a very deep into the future, like 10 or 20 moves ahead. Or you can also explore a lot of options, because you have a lot of pieces to move. You can move all of your pawns, all of your bishops, everything, right? So this tree can get very complicated very quickly, and it's recursive, and it gets complicated. So you have a few optimization tricks that you can use. One that is literally a no-brainer, right, is called alpha-beta pruning. So the idea is, I'm not going to go into it in detail, but the idea mainly is, if you have a tree and you have one branch that's really good, you're not going to explore the other branches in that tree. So you're already cutting down a lot of the branches that could come from that, because you already have a really good movement. So you're going to speed up your progress. Also, this gets even better with other optimization movements. Like if you prioritize exploring some movements before others, so obviously, if I move my queen here, I'm going to put him in checkmate, so that's a really good move. So I should probably explore that before I move a random pawn somewhere, right? So we also have some other optimization tricks. I mentioned this one before, position priority sorting. So you make a little algorithm that says, okay, maybe some movements are better than others. We should explore those before the others, and that way we'll get better results. So you obviously explore maybe your king moving, maybe your queen moving, instead of some random pawn at the other side of the board. Also, limiting your depth. You can't really go all out, right? You can't explore every possibility, because chess or any other one of these games is really long, and you can take 100 moves or 1,000 moves before you actually win. So you're going to say, hey, look, you're going to limit it to 5 moves. I'm going to look 5 moves ahead, and then we'll see if once we move there, right? And also, you can prioritize some movements to go deeper than some others. So for the first few movements that you already know are probably going to be really good, you can explore to depth 7. And then some other movements that are not really that good to care about, you might do just depth 3, depth 2, and just see where that goes. Usually you prioritize the ones that are that seem the most logical, that seem the most favorable to you. And then one thing that's really good and it's really helpful is a transposition table. So what you do is you are exploring future moves, right? So you're doing a lot of calculations for a lot of movements. A lot of the times you're going to explore the same things over and over again. Like, if I move this knight here, okay, that's a bad move. But what if I do it again? What if I do it in another branch where I also move the knight here? You're doing these things over and over again. You've already done the effort of evaluating. So you can create a table where you say, these are all the movements I've tried. This is the score I've given them already, so I'm not going to do them again. So you already know the scores, and you do that much more quickly. So you have a bunch of tricks. You have a bunch of things to optimize your code. But the main idea is you have two variables, two sort of levers to pull when actually doing this algorithm. You can optimize for depth, or you can optimize for the amount of pieces, the amount of movements you try. But the more you do, the longer it's going to take for your AI. So it could go 1 second, 2 seconds, 10 seconds if you have a very big tree, 5 minutes, whatever you want to do. And obviously the better, the more movement it does and the deeper ahead it looks, it's going to be better. It's also going to take more time. It's going to take up more resources of the computer. So it depends on what you're trying to do. So some main takeaways from this, right? MiniMax is a model that allows us to make an AI for 2-player games where it's zero-sum, so either you win or I win, not really anything in between. And you create a decision tree where you explore all the options you have, right? And then you score some things. You want to maximize your winnings and try to minimize their opportunities of countering you. And you always assume that everyone is playing optimally, right? The evaluation function really is the most important part of the code, where you actually evaluate what is going on, how well am I doing. That's pretty tricky to nail. And then also alpha beta pruning, you should do it always. It's a no-brainer because it just speeds up everything with a few lines of code. And also, well, as I mentioned, depth and the order you try the moves out, that is really the most important part of it. So I think that's all for me. Thank you very much for listening. Any questions, anything to add? Thank you. Yes, the handsome gentleman in the back, yes.
All right, my question is, I know how we can use games, but what about like real life?
What do you mean by real life?
Is there tasks that's been solved, like, I don't know, stock trading or something else, and you can use this algorithm to increase your chances?
Well, it's a really powerful algorithm, but the problem with, like, it has its limitations, and some big ones, because as I mentioned, you really can't apply to everything. It has to be like a 2-player thing. Even if you add a 3rd player, it messes you can't really use the algorithm. It has to be where you know all of the information of the board. So if you're playing one of those strategy games where you can't see the whole map, you can't really, you need to see the entire board. You need to have all of the pieces and know where they are. And it has to be an win all, lose all type of thing. So I can't be like, oh, I won 70%. No, that's not really how you optimize for this algorithm. So it has some really big constraints that prevents you from actually applying that to other, not even stake trading, which is even more complex, but even other games that have other mechanics that are a bit more complex. So it's really, you can use it for video games, but it has to be not only board games. but it really has to fit into those constraints, and it actually has to be able to fit into the algorithm. So it's a really powerful algorithm. Again, it was used to beat grandmasters in chess, and you can use it for Go, which is a really complex game. So there's a lot of really interesting approaches with it, but I feel like anything aside from games or maybe a few, because real life applications, I feel like unless it's games or something similar to that, it'd be a difficult fit. So, yeah.
So you mentioned, you explained to us how to optimize, but I'm not sure you touched on this, but the cost or the benefit or like the score,
Right.
like a particular move, how to optimize for that? That is itself like a separate task, isn't it?
That is a brilliant question. That is the most important question, really, because when we're doing evaluation functions, again, it's the most important part of the code. Like, really, there are two important parts, because the algorithm, like, that's it, right? That's the entire code. You just program it and you put it into your system, and that's it. But the two functions you call, which is board static evaluation and get positions, those two are going to be the ones you try to optimize for. And there are various strategies to actually score your systems, but it depends on the game. So it depends on what you're doing. For chess, this is a really easy scoring system. Like, oh, if I have more points, then I'm probably capturing more pieces, so I'm probably winning, right? But you could also say, okay, I could do that and also add patterns. So if I'm doing a checkmate, or this position will always be beneficial, you could make it even more complex. Chess, it's easier because you can just do points. But for example, games like Go or Gomoku, where you don't really have a scoring system, and really it's about detecting patterns, or where if I put a piece, I can capture the entire board and stuff like that. You really need to make functions to look at those patterns. So it would have to be a game-on-game basis, right? So tic-tac-toe is a very easy game to optimize for, but probably Go or some other game is harder, and that just is an entire branch on itself, which goes a little bit out of the scope for this one. I did program like an actual game using Gomoku. So I made the program in C++ where the AI plays against you, and there's some functions that optimize for patterns, and there's a whole scoring system. But it's different. It depends on the game. So but it's the most important part of the program for sure.
I guess I asked this question because if you see what DeepMind did with AlphaGo, and before that, whatever it was, the one that won a chess, right?
Yeah.
It was basically not using these heuristics at all, right? It was learning its own values for the different moves, and those values weren't predetermined, deterministic, like, okay, that a pawn is worth as much and a king is worth as much.
Yep.
It's like, in this context,
Yep.
I think I get a different score, right? It's not as simple as a one number.
Absolutely. Yeah. That you're spot on. And actually, there's AlphaGo and there's AlphaZero. So So the difference is AlphaGo plays Go, right? But it learned from human moves, right? So it was like, oh, let me take all of the best moves from all of the best players and learn from that. So it played very much like a human. And you could sort of counter it like a human, because it's like, oh, well, it does the same moves as the best players do. But then AlphaZero, the zero is that it learned from no one. So it just, by trial and error, learned by itself what are the best moves. And people described it as playing against an alien, because he did things that you wouldn't even think of, because he just thought of this. It's like, what happened? Well, he's beating you right now. So a lot of the times, and it also comes for this, you could probably train neural networks where you don't necessarily tell it what patterns are important, but he figures out what patterns are important. And I'm sure there's a whole branch of different things you could try, different approaches to how many AIs do you, how many neurons, how many different layers, hidden layers you can put on the perceptron to actually make that happen, for sure. For this example, we're doing human level heuristics, but the heuristics function is very important. I'm sure Google or IBM used a deep neural network for that sort of thing. So yeah, absolutely. Thank you very much for that. Any other questions?
Yeah, I have a question.
Yeah.
Is it ethical to use this approach for self-driving cars, for example, just to, evaluate whom to hit? If you see two objects, for example, like a child and an old man. Yeah. Because, I see how it could be applied for this kind of situation, but is it ethical?
I reached the point.
To be honest, I don't really see how this algorithm in particular can be applied to, because one thing is reinforcement learning, and that's self-driving and everything.
Yeah, but if you need to make a decision, for example, if a car sees two objects, like a child, an old man, and a dog, for example, there is a hidden way, like to turn to the left and kill the owner of the car. You need to evaluate all those moves. Is it okay to use this already?
You're putting a complicated scenario, but I think that really it doesn't really apply for the MiniMax function particularly, since it's more of the evaluation function that so the board state evaluation. So you make an evaluation of the current situation, and you're like, okay, so what do we value more? I feel like you would probably do well, if you're doing driving, you're not making the rules yourself, you're probably using a neural network for that. Is it ethical? If that is the question, I'm not really sure how to approach it. I feel like also the AI will make the decision for you, so it's not really a question of should you choose. It's going to be, I trained an AI to do stuff, and then the AI made a decision, and then it's not an easy position to be in to choose between different people. So it's a tricky question, that's for sure.
Yeah.
I would say, sure, it is ethical. Why not? Yeah, but it depends, and also the evaluation function it depends on what the AI is trained on as well. So
Because probably there are some people who are making those decisions right now or making those evaluations.
yeah, absolutely.
Yeah. I don't envy them. I don't want to be in their position.
No.
Yeah, one more.
Yeah.
There was I heard some speech about quantum computers, and lately they became a game. So I was wondering, will quantum computers, if they will become real, be able to use MiniMax algorithm, or they will work in a different way? Because from my point of view, it seems like it's really good connected. So what do you think about it?
That's a very interesting question. I feel like quantum computers just, I'm not really an expert on this side, but I feel like they more or less try everything at once, because they can, have many positions at the same time and reach a solution just like directly. Like if you're looking at a maze, they just like...
So I was wondering, will it use it?
Well, at the end of the day, you're making a decision with the AI right now. So you are deciding to move this piece here or this piece here. So probably, I feel like quantum computing would render this sort of thing obsolete if you can already just like explore everything automatically and reach the best solution. I'm sure there also have to be optimization stuff, because you can't really, well, I don't know, quantum computing is a real thing, but I feel maybe you can't explore everything automatically, or maybe you can, I'm not really sure. But if it's possible to actually just go through the entire tree and all of the options and every possible counter to every possible thing, yeah, you would just play absolutely perfect, like mathematically perfect every time. Since it's not really been tested and proven, I'm sure when the technology matures, you'll have research and studies that actually try it. But yeah, my prediction is, if you get quantum computing, then this is all completely irrelevant, and it'll be in a museum of being like, this is how they did it in 1997. Yeah. So yeah, pretty interesting question.
Okay, thank you.
Yeah.
So I understand that if you make the depth higher,
Yeah.
then your AI will play better, right? That's the right understanding.
Right.
And then I was wondering, you mentioned this evaluation function,
Yep.
right? And I guess that for each of the famous games like chess and so, there's like people have found out the best or a bunch of the best evaluation functions for those games. Right?
Yeah.
So I wonder, if we take those evaluation functions and we tweak them in funny ways, would the AI also play a little funny? Like it would make strategies that we don't think about and this kind of thing.
Right, that's really interesting. One of the things that I did for my project was we made an AI, we tried to make it as best as we could, and that was the hardest difficulty, where it supposedly played perfectly and won every time. And you cannot win, right? Because it explored very well and it was a very good project. So what we did was we had difficulty settings. So what we did with the difficulty settings was you would make the AI drunk. So it would make a choice and then you'd be like, no, do another one that's less good.
unpredictable.
You add randomness to it. You add noise, so you make it do bad choices. It's like, I want to do this very good move, and you're like, try something else. So it depends on the level. So you had, difficult, normal, and easy. And easy, you were just like annoying it all the time, being like, choose something horrible, or randomly choose something. And sometimes literally choosing randomly is a strategy for it playing horribly. So you could probably tweak it and get it to like, that's actually a legitimate strategy to make the AIs play badly. Could it actually be a benefit? I don't think so. Because if you already have an algorithm that tries to, again, you can optimize it better or worse, but if you make an algorithm that does it perfectly, then yeah, it doesn't, like, you would only try make it choose things that are worse. So you would only be annoying it. But we did use that for difficulty settings. So
you could make it like when you play chess, you want to kill the king.
Yeah.
If you cannot kill the king, then you try to kill the queen, and like that, right? Which is your evaluation function.
Yeah.
You could have an AI that goes crazy about your towers.
Capture all of the towers, and that is its main priority. Yep, yeah. And that's literally the scoring system that we have, and you could do that for anything. You could prioritize the pawns, and the most important part is killing all of the pawns. Yeah. You could have fun with it. Yeah, absolutely. Yeah. That's a really cool question. Are we all acquainted? So.
Yeah, let's start.
Yeah. Thank you.